Welcome to the course on power electronics with wide bandgap devices. Today I will continue discussion about the heatsink. So in the last lecture I have shown this particular circuit diagram. So where this heatsink model is given. So in this, the device is modeled using two different models I have discussed, Cover and Foster. So this Cover model is used here in order to design the device. So you can see here in the left side the device is given. So this device is now modeled using different resistance and capacitances. So now this different resistance and capacitances you can see here, this RTH1, CTH1, like this RTH6, CTH6. So these are the different combinations of resistance and capacitances. And from device what we can get? We can get the power loss component. So the power loss component which is given in terms of PVT, so which is equal to IDT and UDST. So IDT is the drain current and UDST it is the drain voltage. So this power loss now it will pass through different combination of resistance and capacitances which is part of the device. So device is modeled in this particular way. Now Tc is the temperature which we can sense from the device, which is basically the case temperature. Now this Tc we can actually connect to the external heatsink. Now external heatsink again we can represent in terms of the resistance and capacitance. Similar way as we can represent in terms of resistance and capacitance inside the device. So basically the resistance, these resistances and capacitances, these are actually different resistance and capacitances of the device. So this will dissipate some amount of heat which I have already discussed in the last lecture. So this heat after dissipation, whatever heat we can get, so that is the case temperature. But the junction temperature T1 it will be different than that of the case temperature, because case temperature will be lower than that of the junction temperature. So that is why in order to find out what is the device junction temperature, we need to have information about these different resistance and capacitances so that we can get actual temperature which device is actually facing in the junction. So if that junction temperature we can actually use, then it is okay. Otherwise we have to connect heatsink. Now what is heatsink? So external heatsink it is shown here. This is also combination of, let's say this is R and this is C, combination of R and C. Now we can have different types of heatsink which will give us different resistance and capacitance, and based on that we can actually decide how much heat we can actually dissipate using this external heatsink. Now this external heatsink also it is shown in different resistance capacitance combination, and this T ambient you can see here, this is the ambient temperature which will be the temperature of the device along with the heatsink after dissipating through different resistance and capacitances. This ambient temperature, generally it is basically room temperature we need to consider. So this temperature it is actually going to be the temperature after connecting the heatsink. Okay, so this T1 and T ambient it is very different, because T1 will be higher than that of the Tc, whereas Tc will be much higher than that of the T ambient. Okay, so in order to maintain the ambient temperature to the device wherever it is connected in PCB or in the module, then we have to connect external heatsink. Now in order to make this equal, so basically we can ensure that the case temperature it will be equal to the ambient temperature. So we have to connect a heatsink so that it can take off the heat, whatever heat will be more than T ambient which is generated due to the power loss in the device. Okay, so now you can see there are different types of heatsink: active heatsink, passive heatsink, hybrid heatsink. So passive heatsink it is basically the fixed kind of device, which you can see in the previous diagram. You can see the combination of resistance and capacitance. So you have probably seen, so basically in the device, so if I need to consider this passive heatsink, so along with the device this heatsink will be fixed. So generally you have probably seen the heatsink which is having different like thickness, and then it is like having different airflow. There like different types of air can flow in between. So now this thickness of different teeth and then the spaces in between, which can be different for different types of the heatsink, but this comes under passive heatsink because this is fixed in nature. Once you select, so this will be fixed and it will have fixed type of resistance and capacitance. Okay, so it is not variable. Once you are connecting to the system, so whatever resistance, so basically whatever resistance it will give equivalent resistance and the equivalent capacitance, it will be fixed. So this is with respect to the passive heatsink. Okay, so this will be fixed in nature. So if the power dissipation is more or voltage and current, all these parameters are changing and that is causing different power dissipation at different time or loading condition, so then also it will be fixed and the heat dissipation will remain constant in this. Let's say heat dissipation in this particular kind of heat sink is 50 watts. So then the heat dissipation in low power loss also it will be same and high power loss also it will be same. So if there is a transient situation where very high power loss is happening in the device and we need to take off very high power, so let's say around 100 watts within very short time, so this kind of heatsink will not allow us to do that. So then what we can do, we can look for other types of heatsink. So this kind of heatsink along with some additional factor, so then we can look for active kind of heatsink. So what is active kind of heatsink? So basically this active heatsink, it utilizes some additional factor. So additional factor, what it can be? It can actually utilize forced air. So forced air, how we can utilize? So basically along with heatsink, if we can connect, let's say small fan, so then what it can do? It can actually force some air through the heatsink so that whatever gap is there in between different teeth, so then heat can actually be dissipated in this. So basically it can take off the heat from the heatsink through the force air or to increase the fluid flow across the hot area, improving the heat transfer. So this is one of the ways, and then they use a fan, blower or other forced air mechanism to drive air across the heatsink, increasing cooling capacity compared to the passive heatsink. So the cooling capacity of active heatsink is more. Now this fan speed also can be variable. So depending upon the type of heat dissipation or maybe like kind of heat dissipation we need to include in the system, based on that we can actually change the fan speed. So if heat dissipation is required more for some time, so then fan speed can be more so that it can take off more heat. If heat dissipation is less, then fan speed can be less, then less heat need to be dissipated. Okay, that way it can be regulated. Okay, the forced air flow replaces hot air around the heatsink with cool air, allowing more heat to be dissipated. Okay, now these active heatsinks are more effective at transferring heat away from components that passive heatsinks require additional power components like fan. Okay, common applications include cooling high power components like CPUs, GPUs and power electronics. In CPUs probably you have seen, so there is already a fan which is connected along with the actual heatsink. So this fan is always actually on, so it is taking off heat from the CPUs, okay, through the heatsink. So that way we can use active heatsink. So active heatsink is much more efficient than that of the passive heatsink, because we have one active component along with the passive component. Okay, so the another thing is that hybrid type of heatsink. So in hybrid type of heatsink, so here we have combination of both active and passive. So active heatsink means like only active component will be there. Passive heatsink means only passive component will be there. In CPUs it is like hybrid combination. So basically it will have passive and active component both. Okay, so these two components are there. So then we can have a hybrid kind of heatsink. So this heatsink obviously much more efficient than that of the passive or active heatsink, because we have both the components and both will be equally utilized to take off the heat from the device. Now this is the external thing, but how we can know that what will be the heat generated in the device? For that, what we need to do, we need to model temperature dependent component of the parameters which we have in the device. So now generally in power electronics, what happens, either people focus on the converter or the control part, but the thermal modeling part, it is generally overlooked, but it is very important part, because thermal modeling can only give insight of the device how the temperature of different parasitic parameters are varying, and what can cause the temperature in the device to increase or go beyond the limit which is given. Okay, now this temperature dependent parameters, if we have to consider them, there are actually different parameters. So first is that the mobility. So basically both bulk and surface values are critical. So this appears in the MOS transistor channel model. So all these parameters are related to the device. So we can just go through these different component, and the device modeling part is not included in this particular course. So that can be covered in other course. So right now I'll just give you the idea about what components are included in this temperature model. Second is the threshold voltage. So this is important or significant for this MOS transistor channel model, because threshold voltage can also be variable with respect to the temperature. So that is why we need to model the threshold voltage with respect to the temperature. Then the important thing comes with respect to drain resistance and the capacitance. Now this resistance and capacitance, generally we consider it is fixed kind of device, but these are not fixed, these are also temperature dependent. So with respect to temperature, the values of the drain resistance and capacitances are also variable. So these oxide capacitances have a negligible temperature coefficient, okay, but the junction capacitance assume constant over the operating temperature range. The Miller capacitance has minimal temperature dependence due to the drain resistor voltage drop. The drain resistance is temperature and electric field dependent. So this drain resistance mostly gets affected by the temperature, but the capacitances, they do get affected, but the variation is not that much. Now there are actually effect due to the electric field. So electric field effect, if you see, they neglected in normal operation since it is having significant only in the saturation. In non-saturation, the electric field is low and keeping mobility constant. Now bulk mobility temperature dependence leads to increased resistance with rising temperature. So this electric field is going to affect the mobility. Okay. Now dynamic simulation of inherent heating. It requires interactive coupling of the thermal description with the MOSFET model. Now the thing which are of our interest, that is instantaneous power dissipation. So the instantaneous power dissipation, how much it is happening? The previous thing, it mostly comes in the device part, So that need to be covered in separate course. So but in this particular course, what we can find out, the power dissipation. So this is determined by the current and the voltage. So ID and UDS. So this current dissipation, whenever we have, at least we get the maximum power dissipation, and from there we can get what will be the temperature in that device junction. This proportional current is fed into the thermal equivalent network. So this the current, whatever we get, so that can be fed into the thermal equivalent network to find out what will be the temperature rise. Now junction temperature node. It provides momentary junction temperature and interacts with temperature dependent parameter of the MOSFET. So once we have this power losses, and from there we can get the proportional current, and which give us the junction temperature, and this junction temperature, it provides momentary junction temperature. So once the current is increasing for transient time, so then it will give the momentary junction temperature which will be during that particular time. So during the transient time, if there is a high power loss, so that will give us high junction temperature for very short time. Okay, sometimes it happens that this temperature, whenever it is arising, if it is within the specified time range, then the device survives. Otherwise, generally this kind of temperature can destroy the device. So that is why it is important to find out that how much maximum temperature we can allow in the device. Accordingly, we need to design the heatsink so that the temperature can be taken off from the device. Okay, so now all this heatsink you know about, so that already are in use for silicon devices, means active heatsink, passive heatsink, hybrid type of heatsink. It is there available in all the consumer electronics, and in laptop also, like you can see in the CPUs or computer CPUs, laptop or computer CPUs. So you can see this kind of heatsinks are there. So if you try to open that and see that heatsink, what kind of heatsinks are there, you will be able to see different types of heatsinks available. Okay, now these are there for silicon devices. What about wide bandgap devices? So where we need to change for wide bandgap devices? So generally all the kind of heatsinks which are available, so they are generally used for silicon devices, but for wide bandgap devices the situation is bit different. So that is why, due to their property and everything, as you already know what are the differences, so then we have to look for alternate solution. What can be the alternate solution? So can we really use this heatsink, or we have to look for other solution? So basically wide bandgap devices, there the temperature variation, so it is actually much different than that of the silicon devices, because their operation at high frequency, and also these kind of devices are like much more compact than the silicon devices. So that is why the type of heat sinks need to be used for this kind of devices must be much more compact than that of the passive heat sink which are available. So this kind of compact heat sink which should be much more efficient to take off the heat, so that kind of heat sink we need to look for. So the both active and passive, that actually takes like quite large amount of space in the system. So that is why we can look for alternate solution. That alternate solution can be using the phase change material. So what is the phase change material? So basically this phase change material, it is some material which has the property to absorb heat during the phase transition. So you can see here this phase transition. So basically here, whenever that phase transition is happening, so then what will happen? Let's say this solid to liquid, it is going to solid to liquid, or liquid to gas. So in that kind of condition, so the heat which will be dissipated, that will be constant. So you can see here absorb heat without temperature rise. So in this particular region, basically heat dissipation, heat rise in the device or the system, it will be constant. If we have, so like if we have a heat sink which has the phase change material, so then what will happen during this particular time, the heat dissipation remain constant, or heat generation in that particular heat sink will remain constant. Although the with respect to the time, so basically heat dissipation, so the power dissipation is increasing, but heat generation is not increasing. So that is the property of the phase change material. So we can use this kind of material along with the heat sink. So basically whatever heat sink we have, so generally how the heat sink looks like, so basically you can see any heat sink. So basically if you try to represent it in the simpler form, so it will be having some teeth. Okay, so now this will be connected to the device. Now this is with respect to the passive heat sink. In active heat sink, so what will happen? So there will be fan. In hybrid heat sink, it will be combination of fan plus passive heat sink. Now in PCM, what will be there? So this kind of heat sink it will have some portion of PCM material. So basically let's say, so like if the size of this particular heat sink is such that we can actually replace 1/3 of this particular heat sink size using phase change material. So this is our passive heat sink, and this particular solid portion we can actually connect phase change material. So this is how it can look like. So now we can have like quite significant portion of using phase change material, or maybe small portion. So that is depending upon like kind of heat we want to dissipate. And now due to this phase change material, this small amount of phase change material, the overall properties of the heat sink will change. So you can see here, so this is the property which we are including along with the passive heat sink. Okay, this PCM heat sinks effectively manage thermal stress during the transient overload in the wide bandgap devices. So during transient overload, so that is for very short time. So as I have already told in the previous slide, so in the transient time also temperature will rise for very short time. So in that time, if we have this PCM material, then PCM will get activated and it will keep the device within this particular region. If for very short time the temperature of the device can increase, but due to this PCM gets activated, so the overall temperature remain constant for that particular duration, so that it can actually maintain the device temperature within a suitable limit. Okay, so this is very useful for wide bandgap type of devices, because you know there is like high frequency operation, and it can happen that during transient time or the switching time, so there can be transient overload stress, or maybe thermal stress can be there in the device. So that can be taken off by using the PCM based heatsink. So proper selection of PCM volume is crucial for optimizing the performance, because we can have, because you can see here this is the solid portion, so there has to be enough space so that heat can be dissipated. So if there is a fan along with this overall heatsink, so like heatsink which is based on PCM, so if we have a fan, so there should be space to take off the heat. So basically air can flow through that spaces. So if we have the complete solid block, so then there will not be any space to take off the heat by forcing the air through that particular heatsink. If we have these different spaces, so then only the air can be forced. But if it is completely solid, then air cannot be forced. So that is why we have to see that how much space, how much of this particular passive heat sink we can actually replace by using PCM. So you can either replace 1/3, 2/3, or complete heat sink by PCM. Obviously that will give us the property of PCM, but there will not be enough space to take off the heat by forcing the air through the heat sink. Okay, so that is why it is very much important to select the volume of the heat sink which we are going to replace using the PCM. Okay, that's all for today. Thank you. So more about this I'm going to discuss in the next lecture.